we look at this X, which is T star of Grassmannian of three-dimensional subspaces. Is this on? You can hear me okay? Is it? Okay. Is it maybe higher?
It seems to fall.
Is that better? All right. So what do? We look at the moduli space of two-pointed rational curves and x on some degree d. We look at its virtual fundamental cycle, and we push it forward under evaluation of these two marked points. And so then we get this. First of all, as we discussed, there's a factor of h bar, and then some cycle, which I think I denoted CD, where CD. So we look at now as we look at the moduli space of. So this is my x, and I look at the two-pointed rational curve. Look at the curves of degree d, and this evaluated these two marked points. I go to x squared, and so that would be, of course, sitting. This will be sitting in the product of x with itself over its affinization. But in fact, its dimension is exactly the dimension of this. So it's in the top homology group of this. And this is a union, so this is might be called Steinberg variety. I think the Steinberg I use Steinberg variety as a generic term for varieties like this, although I think the Steinberg variety originally is probably just for the T star of flag variety. And so, and this has, maybe call it like German S, and this has a bunch of reducible components. For example, there is maybe I write it C0. This is the diagonal. So this variety always has a component which is a diagonal. Diagonal is clearly dimension x, dimensional subvariety here. Then there is the next one, which will be the one of interest to us, and then there's the last one, which is maybe I'll write this K. This is just Grassmannian cross Grassmannian. So inside of so Grassmannian is a cycle inside its cotangent bundle. It's compact, therefore it's going to go to point under affinization, and in particular it's a Grassmannian cross Grassmannian is going to be a dimension x dimensional cycle in here, so it's always. So we want to look at this one. So we will explain what it is. Because in fact, the cycle CD for d equals 0, you get of course the diagonal, because d equals 0. Not CD, but in the d equals 0 case, you're going to get the diagonal. That is clear, because if the degree 2 points lie on degree 0 curve, if and only if they're the same. And so this is the one. This is the one we're always going to get. So we'll see that this is CD is in fact proportional to this sigma 1. And so therefore, in particular for d equals 1, this is in fact the locus. This is the locus. These are 2 points what is d equal 1? D equal 1 means a line. So 2 points at line. On the line. So maybe we'll get to this more precise analysis in a second. Maybe I'll say a few words in general. So in general, this sort of analysis is applicable to so what is true in general. So for any x which is an equivariant symplectic resolution. So what's an equivariant symplectic resolution? It's first of all, it's a symplectic algebraic variety on which is a resolution of singularities. If it's so when do we know that some variety is a resolution of singularities? It means when you look at the canonical map from X to the spectrum of global functions of X. So it's an affine algebraic variety. So it's not affine, but it's a resolution of singularities of an affine algebraic variety. So spectrum of global functions, 1x, and the result is x naught. So this is resolution of singularities means this is properly birational. And conversely, if you have x, then it can only be resolution singularities of this variety. So if you already given x, then you know what resolution of singularity of what it is. And so x is a symplectic resolution if it's symplectic. If it's proper, means properly and birational to the spectrum of global functions. And equivariant means you have a group action. In this case, so here I had an action of this equivariant variable h bar that came from an action of, if we denote it C star h bar, the one that scales the cotangent directions. And this group action scales the symplectic form. Equivariant means it scales symplectic form non-trivially. And then in this situation, it's always true that you'll have this virtual class will be divisible by h bar, because the kind of argument we gave with this abstraction theory, only use symplectic form. So you get this h bar factor and then some cycle. That cycle will be always sitting here, and the dimension of this for any symplectic resolution is the dimension of x. So this analysis is the same. This Steinberg variety will split into a bunch of components, and it's always be the case, which we'll analyze in a second. It's always be the case that only very few of them contribute. Like here you could have k of them, but in fact only very few of them contribute. And so, and which contribute is which components can contribute? This is determined. Many components may be general principle. Somehow many components, like somehow most components of the Steinberg variety are ruled out by counting powers of h bar. So we see here, this cycle has to be h bar times some non-equivariant cycle. If you see that the contribution in some component is in fact divisible by h bar square, means in fact it's zero. So anytime you compute a contribution and see it's divisible by h bar square, then there's just in fact it's zero identical. And so let's maybe a more basic example on these lines is that, for example, x, I can take the Hilbert scheme of, say, n points in the plane. So I presume in Kyoto everybody knows what this thing is. I don't have to explain. And if you, if for some reason you don't, you should be really ashamed of yourself. But, and so then this map pi, this is resolution of singularities of the n-fold symmetric product. Right? And what are the components of the Steinberg variety look like? So if I want to so this means so if I have here I have maybe I draw a picture. So here I have some subscheme, and I'll draw a subscheme of the kind that if I have like 3 points come together, I mean, so maybe I'll draw a curvilinear subscheme just to be. You can have like 3 points together on a parabola, and then maybe two points together on some line. Of course, not every subscheme is curvilinear, but and then a point. And then this is going to map to just 3 times this point, 2 times this point, and 1 times this point. So this map takes the scheme and just takes it and remembers only the corresponding zero-dimensional side. And so then the components of the Steinberg variety are indexed by partitions of n. So my Steinberg variety will be a union of n. And what is this thing going to look like? So this means, and in particular, right, the fiber here, so if I have, what's the dimension of the fiber? If I have 2 points come together, then they could come together along some direction. Means the dimension of the fiber is you lose 1 dimension here. And in general, if you have like 3 points, means you lose 2 dimensions and so on and so forth. So then these are pairs. You just fix this partition. So it means you have some pair of size mu1, some partition. So this is mu is a partition of n, some mu2, and so forth. That clearly you have pairs of subscheme that map to the same cycle of some length. So what is the dimension here? You get for every part of mu, you get mu1 for the what's the dimension of the fiber in the first factor, plus you get mu1 minus 1 for the dimension of the fiber in the second factor, plus you get 2 for where that point is where this point is located. Right? So each mu contributes 2 mu I. And so you sum them up, you get exactly the dimension of x. The dimension of x is and now I claim that that only sigma that corresponds to a partition of a single part of length n contributes. The quantum product to CD, to any CD. And what's the argument? The argument, well, suppose I have a curve, and so it has to be a curve in the fiber of this map. But then, if I have a curve in the fiber of this map, then it means so you have So I'm trying. So there's x and there's another copy of x. So maybe I'll draw. So it means this scheme somehow changes. So maybe this rotates and this becomes some different curvilinear. We have a curve in the fibers of this map. Any curve will be contracted by this map. So if we have a curve that sits in the fiber. But then, see, a curve in the fiber in this map is really a product of what happens here and what happens here. I mean, it's a curve in the product. Because there's no way, this subscheme has no way of interacting with this subscheme. The Hilbert scheme is really a product of two smaller Hilbert schemes here. So you have two. I mean, if you have more than one part, then you have two independent ways for them to interact. And that means each one of them. So if I have a curve in a product of symplectic variety, and it's non-trivial in each factor, then each factor will contribute h bar. And so that thing just vanishes. And then there is a separate computation. There is a separate computation to do this computation. But we're not going to do it today. I'll explain some principle by which can be, I mean, the principle by which I'll explain how done is Grassmannian can also be applied for the Hilbert scheme of points. And so for Grassmannian, a different principle will be used. And so for Grassmannian, we'll see which curves contribute. We will use equivariant localization to compute this push forward. One could, in principle, look at equivariant local. I mean, one could, in principle, compute this push forward by equivariant localization. Equivariant localization, which I spent some time discussing yesterday, it's a very powerful tool. In principle, one can do this computation. Much better, however, to combine it with this analysis, because if you really compute it by localization, then at the end you'll have some magic identity, with many terms, and in the end there's zero. So it's always best to think a little bit ahead of time. So only compute the terms you really need to compute. And so it means general true in equivariant localization. You don't use equivariant localization, very powerful tool, but don't use it blindly, because otherwise you get much more you do much more complicated computation that you need to do. So equivariant localization on, or maybe for the action of A on the right. Nobody pointed out that this is, strictly speaking, I said something incorrect here, and the correct thing. So think about it. This is what I've proven is this curve's really non-trivial as long as you have more than one marked point. More than one point came together. Because if for some this point is 1, that is okay. So you can have some parts equal to 1. So authorization for the action of on my x, or maybe I'll restore to T star Grassmannian. This is my x. For A, this is the diagonal torus A1 to N, subtorus in GLN. So we're computing a push forward of some cycle, and that push forward, like we discussed before, you can always compute by localization. Means you just push forward from the fixed locus but what you can pushing for the fixed locus, there's some contribution of the normal directions to the fixed locus. You get there? And so what are the fixed loci? So M 0, 2 X D. What are they? Well, how can a curve? So maybe the first thing is to think about what are the fixed loci in X itself. Well, so in X itself, I claim first of all that this is just the fixed loci in the Grassmannian itself, and then this corresponds to coordinate subspaces. We discussed fixed loci in Grassmannian itself. It correspond to maybe span, i.e. span some subset of coordinate vectors, where I ranges of k in a subset of 1 for m. And there is if I have a fixed point isolated in a variety, that means my torus acts with non-trivial weights in the tangent space to that point. It acts with non-trivial weights in the tangent space of the fixed point. It acts with non-trivial weights in the cotangent space. And therefore, in the fiber of the cotangent bundle, there can be at least only one point, the 0 point. So whatever fixed point here has to project here, but then in the fiber of this map, there's only one fixed point. And so if I have now I have a map from a two-pointed curve to some variety. So what can happen? So here I have maybe my two-pointed rational curve, and I draw some example of such. Maybe this is one mark point, and there's another mark point. So where can it go? So this is my, maybe I'll draw X in curvilinear way. And so X, by my assumption, has some isolated set of fixed points. Maybe these are the fixed points. Something like this. And then a marked point can only go to a fixed point. It's a point. So if it's fixed by, if the map is fixed by a torus, it means this guy goes to a fixed point. Maybe I'll draw this. And then some components. This one also goes to a fixed point. Some components of this curve can also just collapse to a fixed point. So maybe. This is okay. This is okay for this component to collapse because it has three marked points. But some components don't necessarily have to collapse, because you see the torus that acts here, we consider maps after multiplication domain. So a torus acting on X, its action on the image may be compensated by the action on the source. So it can be the case that some component goes to a one-dimensional torus orbit. So it could be that if there's a one-dimensional torus orbit, then some rational component we can send there. And then this maybe I'll use different colors so that to be clearer. So like this one goes maybe, I'm about to take this point to be blue. So this blue has to be, since this is a special point, has to be fixed. And then another component, maybe go to a different orbit here, to a different one-dimensional torus orbit. Then this whole thing, maybe keep it red. This can be collapsed. So this just goes to this, and then this white piece just go somewhere else. Okay. So now the components of this map that are not collapsed by the map, the components of the domain that are not collapsed by the map, have to go to the one-dimensional torus orbits. And components that are somehow components that are collapsible, they have to be collapsed to fixed points, and then the nodes and the marked point have to go fixed points. So you have so in the target you have a configuration of fixed points and one-dimensional orbits, and you can draw like a tree in that configuration. That clear? So what are these one-dimensional? So fixed points we discussed. So one-dimensional torus orbits. But if we look, I claim they're also isolated. Something in fact very simple. So so if we look at the tangent space at a fixed point, maybe call it. So maybe call this point P sub I. So we look at this point P sub I to the cotangent bundle to my variety X. What is the character? What is the character of that space? Well, this is the home from the bundle to the quotient plus dual. Okay. And this has weights. Maybe I'll write it like this. So this is if my AI. So this has weights. Like this is the character of that is summation aj minus ai over j not in I in I plus this h bar. Sorry, the character would be. I should write the character multiplicatively. aj over ai plus the same thing for the dual, so h bar inverse summation ai over aj. In other words, the only conclusion from this is that this torus here, these are distinct. So these are distinct. And so at the marked point, one-dimensional orbit can only go in the direction of this coordinate subspace. I mean, only in the direction of one of them. These are they. So if I have a vector space, and I have a torus acting with distinct weights, then the one-dimensional orbits are just the eigen directions. And so these orbits are only of the form. So if this is my point pi, then what I can do is if I choose one of these weights, let's call aj over ai, well, I'm going to get to the point p, so to speak, I prime, where I prime is where I take I add j, and I remove I. In other words, the two fixed points lie on a one-dimensional orbit if and only if they differ by exactly two elements. You know, two k-element subsets, they cannot differ by one element, but it can differ by two, and these are the one-dimensional orbits. This is also. And this is one of the homework problems. This is also a line in the Plucker embedding. So a line in the Plucker embedding is when you have two linear subspaces lie in a line in the Plucker embedding if their intersection is k minus one dimensional. So now we would like to now the weight of the compute so so when you so if you have a fixed point, then you compute push forward. You have to divide by the so remember saying K theory. Well, in K theory, if we want to compute like the Euler characteristic of some sheet, that was we're summing. So say we're summing over some variety, which is in this case moduli sheet. So we sum over fixed points. So let's say assume fixed points are isolated. So P, maybe call it left. Fixed points F in NA. You compute the Euler characteristic. Well, it's 1 point thing. So this is you don't have to take Euler characteristic. It's just a restriction of F to that point F. And here you divide by product of 1 minus W inverse, where W inverse are the weights of the tangent space at F to my modulo F. And so what we're going to compute now is a difference in two ways. So this is differs in two respects, that if you is this for m being m of 0 to x some degree d. First of all, the tangent space, this becomes virtual tangent space. Which is the difference between the deformation at F and obstructions at F. And so its character, is now the summation of some Wi's minus some other, I don't know what's it called. I don't know what it's called. New i's. And then since we're computing not in K-theory, we're computing in cohomology, we just get a product of the, in cohomology you imagine this W is exponential of your cohomological variable. So 1 minus 1 over W becomes just W, and then there'll be VI, there'll be VI. So the weights of obstruction go in the numerator, the weights of deformation go in the denominator. And now we want to, in particular, in this obstruction piece, there'll be some weights that are h bar. Like one of them we already identified. And when we would like to understand this obstruction, we would like to see what is the overall power of h bar by which this thing is divisible. Because we like anything which is divisible by h bar square, we just discard. And so okay, so what are these deformation abstractions? Well, the deformation of abstraction, we discussed what this is. These are the, so first there's a deformation and abstraction that come from deforming a map from a fixed curve. So and then there's I write a deformation of the So there's a deformation of the domain. There's no obstruction to deforming a domain, plus deformation of the map minus the obstructions to deformation. The map. And this part here, this is the cohomology of the pullback of the tangent bundle. And inside this, in the abstraction piece here, we found this H1 of the cotangent, the tangent to the curve itself. And there was this piece that this was a trivial piece that had this non-trivial occurrent weight. There was discussion yesterday. And so now what I want to point out, this is qualitative, is that now for every component here, there will be a power of h bar. There's a power of h bar for every component. So for every one of these will give me a power of every one. I mean, the collapsed one, it's this different because this, for example, this marked point will kill that. Will kill. Don't worry, but these ones, the two-pointed ones, this is for every component that contributes. So this contributes h bar, but it really contributes h bar to the number of components. And then you can ask, well, maybe this means that the curve can never break. But that is not true because you see there's in here, you can get a power of h bar in denominator. And so, because this is what is the deformation of the curve? The deformation of the source, if we have a nodal curve, the deformation of that are just the smoothing of a node. And so, if I look at the locus so maybe abstracted. So if I take inside some, let's be not super specific. You look at some, in fact, even like a stack of curves. You don't have to be. I mean, this is a very general statement I want to make, and this is not. So inside of that, you can look at there's a divisor of reducible curves. So you have curves of the, somehow there's some curve general element here. General moduli element here, some curve. I'm drawing like a homogeneous picture of that. Inside that moduli, there's a divisor of curves that break. So here, a point in here is a union. So you have one component and a union another component. Not one. And then, so this is the divisor. So the normal bundle to this divisor, what is this? What's the normal bundle to that divisor? So if we have, means on each component you have a marked point, because this is where they join. And then you have, so this may be, so let's not get confused with this complex picture. And then there's some smoothing of this. So. Something like that. Some smoothing of that. And so this is, right, so there was some curve C, and it broke into C1 and C2. And then there's, then the normal bundle to this divisor is in fact the tensor product of the tangent of the tangent line at the point P to the curve C, tensor the tangent at the point CP. This is the line, and that line is normal to this divisor. And why is this? Because the smoothing of the node is just the local model of that. Is to take x, y equals 0 and replace it by x, y equals epsilon. And the weight of epsilon is the product of the weight of x and the product of y. And so from the smoothing of the node, there is therefore a term that is the weight. So this has the weight of, so this guy produces the weight, one tangent weight plus another. And in fact, it gets more complicated because this, so more complicated, the complete truth of that is that this map from here, so what was that? From here to there could have been a multiple covering. It could be that this map from here to there is some G1 to 1 covering. This could be some variable Z here could be going to Z to the G1 here. And then if there's similarly, you take G2 to 1 covering there, then the real tangent weight, so if you have a tangent weight, which was my, so maybe so there's some weight W1 and another weight W2. So this V1 is really A J over AI, but let's not worry about this. And so the weight is not really V1 plus V2 because the weight to the curve is V1 divided by this D1. So it really is G1 divided by G1 plus V2 divided by G2. So if this guy may very well, in general, this guy may give you H bar. There's no reason for this not. And so then there's a definition of, so if you count, but this could be only, you can get only, so you could get at most 1 H bar per node. And so then and you count the powers, but the point is that you don't get, so like if you try to smoothen this node here, you're never going to get H bar because this is the weight. You only get some of. So how does it go? So maybe I'll get to the so maybe definition. A map stable map M in M G2 bar X D A is unbroken if one of this is true is either it maps to the fixed locus, or it is an unbroken chain deform, so you have some fixed point. Get some colors. Fixed point. With this being my first mark point, this is my first mark point, so this is f of p1. I'll just write first mark point. And then the second mark point. And the tangent weight at every junction, so there's some degrees d1, d2, and the tangent weight w1, w2, then d1 over d1 plus d2 over d2 is equal to 0 mod h. Means it's just equal to 0 since h is not the weight of a, you just say equal to 0 as the weight of a. I'll just keep mod h. Or you have the same thing except you have a collapsed component. Then you have your marked points sit here, and then you have an unbroken chain. And so then this power counting for h bar says that everything which is not an unbroken map contributes a power at least h bar squared. And why is this? Maybe we can. I mean, it's easy to see, but let's just analyze it here. Well, suppose you had more than. Suppose you had a. Let's for the sake of the argument assume that maybe you have a tail. Here's your marked point. And so this is maybe I'll for let's try to distinguish marked points and fixed points. So you have a marked point sitting atop a fixed point. This. So let's suppose there is, so this is marked point. And then there's just a fixed point. Fixed point, fixed point, fixed point, fixed point. And suppose you got to the second marked point, and then but you still continue. You don't terminate there. You're like that little chain. So what will happen? Here you have, your marked point cannot be a node. And so what really happens in your curve is that you have in the domain of the curve, you have one more component that gets collapsed by this map. So it looks like this. And your marked point is really here. It really, the stable map really looks like this. Its image looks like this, but the domain of the stable map looks like this. And then as you try to deform this, so suppose you try to deform it, smoothen this node, then the weights will be, there will be some non-trivial weights from the source and nothing from this side. Because this side is, the weight of that is just 0. Right? So you're not going to get, there's no chance to get this kind of cancellation. Anytime you get like a triple point, or you have a marked point, and then you continue, You lose your ability to get this consolation. Right, this was a very long discussion, but the truth of the matter is that they're the only forecast means observation really. This equation can never be satisfied for Grassmannian. Because these weights are just not, just involve different variables. There's no way to make them proportional, no matter how you multiply them. These tangent weights are, so this concretely you're looking for relations of the form aj minus ai over d1 plus ak minus ai, maybe al over d2, where I and where I and L belong to I, and J and K do not belong to I, and okay, there's no solution to this. Right? They're just not proportional at all. So this has no solutions. So you cannot have a chain. So the conclusion that the only unbroken curves are multiple covers. Well, the ones that collapsed either collapsed. The only non-trivial. Unbroken curves are multiple covers. Once. Anything else you don't have to compute. Because anything else is going to give you something which is divisible by h bar squared. So what does this mean? It means that if you want to compute what the cycle SD in any degree D, this is really just computation for lines with a little bit of yeah. Somehow when you compute so what does it mean to compute multiple covers? Well, to compute multiple covers, it means okay, so there's some yoga how you compute the multiple covers. So if you have your multiple cover, that means your this pullback of this tangent bundle will be something. You have to think what it is. It will be some numerator denominator, and then you can, you'll see that the numerator denominator they've there's some computation I advise you do. In fact, I don't want to do it here. It's not. Maybe I'll put it in the homework. It's the essential part in this computation is when you have a multiple cover, then it has an automorphism, because the map that sends, if I have a map that sends z to this power, then that z can be multiplied by any d roots of unity, and this will be automorphism of this map. So a multiple cover has an automorphism of order d. So if you have a multiple cover degree d, that has an automorphism of order d. And since we're computing the way the virtual cycle is defined with rational coefficients because of the automorphism, is that the automorphism factor comes out. You get 1 over d. And so then the conclusion is that this d is 1 over d times c1. This is something you can. Maybe this will assign as an exercise. And the way to do it is you compute the contribution of one single curve in any one you choose. One single map, any one you choose, and you see what the weights say And then and the only interesting thing will be this D. I mean, there are other ways to do it, but it's maybe best to do it by localization as an exercise. And so this means that this in fact means complete computation, because what is C1? C1 is some explicit correspondence. It's the pairs of points that lie on a line. What does it mean somehow concretely? So remember, so maybe I'll erase this picture here. So X, remind you that X was the quotient of pairs of matrices A, so I have a map CK Cn, and this is maybe we call this one A and this one B, such that B times A equals 0, and A injective where A is 0, more than GLK. And this by the map where you take D was the product in the other direction, A times B was mapping to the set of matrices D such that D in n by n matrices such that D square is 0. And what else? The rank of D is less or equal than K and is -x. So my variety, the components of the Steinberg variety are parameterized by the strata here. So then this has some stratification. Maybe you take the rank of D, could be, well, let's say, and somehow for concreteness, let's say concreteness, let's say that in fact K is equal to n minus K. So then the maximal the rank can be is K, K be K minus 1, and so forth 0. Then since the image of D has to be contained in the image of A, contains in the kernel of D. If this thing is k-dimensional, then there's only one choice for A, and therefore the only one choice for B. So over this sits the diagonal, which we denoted sigma 0. Over this, so this over this sits Grassmann. If D is 0, this A can be anything, so this is the whole Grassmannian sits. Grassmannian. And over this sits what? Sits a pair of so you so this is where this guy is k-dimensional. So you look at so this guy is k minus 1 dimensional. Dimension is something down. Dimension equals k minus 1. And so my whole S1, this is the set of pairs where my two subspaces, they sit in here. So in particular, if I have two, like if I look at just projection to Grassmannian, what does it mean? What are the corresponding points in Grassmannian? The corresponding points in Grassmannian are two subspaces such that intersections of them is k minus 1 dimensional. In other words, these are points in the Plicker line. So this is. And then basic but important observation here is this. Is this correspondence? This is very often the case with Steinberg correspondences. It's really a product of something on one correspondence transpose. So maybe so what does it say? It says I have two points in X, and I constrain them by some intermediate object. Okay? Means I look at the first correspondence formed. So maybe this is I write it like this. So sigma 1 is really a product of some other correspondence, which I'll denote. And it has to do with SL2. I'll denote it by F. F and a transpose correspondence, which is also denoted by E. So what does correspondence F is? So correspondence F, this is a correspondence in so it's a product in my T star Grassmannian Kn and T star of the Grassmannian K minus 1. And what does it form by? It's formed by pairs. So this is my image. So I have a pair. I have a pair here. Here I have a pair A1, B1. Here I have a pair A2, B2. And the correspondence this consists of pairs such that the image of A2 is contained in the image of A1. This is my image of D. And secondly, the operator Z, which is the which is A1 and B1, it's also equals A2 and B2. In other words, this is like a Steinberg correspondence, but for Grassmannians of different size. Since Grassmannians of different size, they can map to the same. So this is, they have, this is maybe my x. And I'll write it xk, and this is xk minus 1. But they both, xk and xk minus 1, they both map to square zero matrices. And we can, so it makes sense to take a product over this map. Right? So this is like this. So this is just the first. So this is just, I'm just rewriting the top half of this correspondence. Because if I have an actual operator, since my A2 is injective, then the actual operator, to know what D is the same to know what B1 and B2 is. And then to find out this whole correspondence, you just take this correspondence and compose it with the transpose correspondence. This is what it means. I mean, what is the composition of correspondences? Is a set of all points such that there is a middle point in this thing. Okay. And so then this is the conclusion is done, and we can write. Again, this is very so in the context of Nakajima varieties, this is somehow more or less automatic. That all these correspondences will be bilinear and simpler correspondences. It will be quadratic and more simpler correspondences. And so how do we write them? This is like a basic. This is the beginning of geometric representation theory. That these two correspondences, E and F, generate a geometric action. L.2 on the homology of direct sum over K from Q to N. This is the beginning of this whole theory of geometric realization of. And so how are we using this language? How are we going to write the quantum product then? So first of all, this is, so if we want to write the quantum product remind you what this, how the quantum product is defined. So the quantum product is an operator in the, say, cohomology of X. So it starts with the cup product. And then there's a term for all non-zero degrees. Zero, Z to the D. And then comes defined an operator, so then we take action of M 03 bar RXD virtual on. Sorry, this is a mixture of formulas and English words, since I don't think I defined the notion of this correspondence on, so you take the first, you take three entries here somehow, you use something, then you plug your class, and then you take some class, then you take the divisor, then you take the lambda class, and then here you take the output. And so this is now, so if lambda is in H effect to the divisor, then this operator by this what's called divisor axiom, but it's really not an axiom. It's a simple theorem about curve counting, that this is a divisor you can take out of this. So this would be, so this what you will get is that you pair lambda with a d, take z to the d, and you take the action, this action divided by cd. You forget that one of the mark points, if you put a divisor, one of the mark points, you can forget it at the expense of this. Okay. And so this cd is 1 over d times c1. What?
H bar.
Oh, right, H bar, right, exactly. Yeah. Oh, no, c1 is, I think, oh, right, H bar. So I get H bar. Thank you, Henrik. D H bar times c1. And so then this d and this d will cancel. I mean, this is something linear, and you divide by d here. And so then what you get, so then the whole thing becomes, so you get still the cup product plus H bar. And now the sum I can take, so that I get the pairing, so I get it by pairing of lambda with the generator, with so to speak, in a curve of degree 1. This is generator. Of H2. And then I get a geometric series, so I'm going to get z over 1 minus z times EF. So I must apologize. I forgot to say when we were discussing. Of course, there's we computed this the case when I was stating the the classification of unbroken maps. There was also the case where the two marked points are mapped to the same point. And so in principle, there could be a contribution from the that of course evaluates to the diagonals. I mean, if both marked points map to the same point in X, then this goes to the diagonal. So in principle, there could be a diagonal corresponding. So in principle, so a very general formula like this is true for any Nakajima variety. So in principle, there could be a diagonal or scalar corresponding. But in this case, it can be shown to be 0 because the, depends on your convention. Usually it's 0. But very often, not usually. So the way that this is found from the fact that this operator, this scalar, needs to, this operator, scalar depends. depends on z. In fact, it's of the form, this factor of the form O capital Z. And this is found from the fact that this has to kill 1 in the H0. In other words, this is a consequence of the fact that if I take the quantum product of anything with 1, then this is just this. And this is it's a general property of quantum multiplication that identity remains identity for quantum multiplication. We take the quantum product with identity, we still get the same thing. And so in principle, I mean, the general formula is true, but in principle there's a scalar here. The scalar is found from the fact that if f happens not, if this lowering operator happens not to kill the fundamental class, then we have to compensate it. So that's a formula. And now this is now we have to remind ourselves what is it we're trying to do. Now we'd like to compare this with the formula. So now want to compare with pinching. And so spin chain, so what was the spin chain? Spin chain was some specific operator that was acting in this specific energy operator. That was like summation over I goes from 1 to n, summation I plus 1 with quasi-periodic boundary condition. And how will the comparison go? So first of all, so what would be the key to the comparison will be a certain quantum group. So go back to again. So the Yangian of GL2. This is, I'll explain what the quantum group is. It's a quantum group. Maybe, so what the quantum group is, i.e. I'll explain what this thing is, the Hopf algebra. Deformation. Deformation of the universal developing of this Lie algebra. Tensor polynomials in one variable. Call it like that. And the relation, so the relation of this to spin chain. This is one fundamental object of how one fundamental field in which Kyoto made a fundamental contribution to mathematics and physics, and namely the way this is connected is that this guy has representations of this kind. And also, it has a family of commutative subalgebra. Has a family of maximum commutative subalgebra. maybe should be called Baxter subalgebras probably. Although it's usually called beta subalgebras. I mean, Beta is one of the greatest scientists of the 20th century, but I don't think he considers this algebra. So I think Baxter is the one who's Baxter subalgebras. Because Baxter didn't have a Yangian, but anyway, he considers so. This is, and they depend on Z, parameterized. By Z, where Z is, generally speaking, it's an element in the Cartan torus modulo center. So which for GL2 will be precisely a matrix like this in GL2. So this is the matrix for the quasi-periodic boundary conditions were parameterized by a matrix like this. And so these commutative subalgebras will go. So there's a this energy operator will belong to the image of this algebra. So this will be saying that this will be a quantum integrable system, and that this particular operator, which we wanted to diagonalize, is in fact included in some very large commutative algebra, which the whole of them can be diagonalized. In particular, this is how some analysis, which will, in fact, I'll try. I mean, one of the goals of my lecture is to get to actual analysis, how you actually diagonalize this. And another fundamental Kyoto discovery is on this side. Is that if I now look at all the ingredients in this formula, well, I have this part, E and F, this corresponds to SL2. But now, if I look, but in this formula, I have not only the quantum part, I have also the purely classical part, this operator here. And if I want to compute the commutation relation between E and F and this operator, then what I will discover already has been discovered, and somehow this is one of the cornerstones of Nakajima theory, is that if I'm interested in what sort of algebra does this SL2 generate together with this element here, I'll find that the commutation relation of this guy with this guy, it will be deformation of the commutation relation of in this polynomial algebra. This guy is like it's a deformed version of like T minus T. So these are E and F are this ones. So this is an algebra of polynomial matrices, and so then this is in the algebra of polynomials where the constant matrices that form the ordinary SL2, and then they're brothers. So you can take. So this together with some center generate. So with some center, this together generate exactly this Yangian. So this in fact. With some central elements, these guys here, they precisely generate this Yangian. And then this element here also belongs. It lands in exactly this boxer. So these are commuting operators. I mean, certainly it's not just one operator, but in general, quantum multiplication is a commutative algebra. So operators of quantum multiplication form a commutative algebra, and that algebra lands into here. So quantum operators. So in these geometric incarnations, the operators maybe I'll write it alpha star, which means quantum multiplication by anything. They depend on Z, and this function Z they come again. maybe this is the key point. I mean, this is maybe I'll say it one more time. This sort of this link between quantum integrable systems and geometric representation theory, which is envisioned by, well, Nekrasov-Dashvili maybe didn't have it in terms quite like that, but certainly in very closely related terms, the link is that that spin chains, integrable spin chains, are quantum integrable system explained by Yangian symmetry. And this representation, right, I forgot to say that this special representation is the same. So this is, if you think of this, what sort of representation of the Yangian does this space give? Is that representation of the Yangian? So this is the geometric statement that if you look at the cohomology, so again the statement, if you look at the cohomology of cotangent bound of Grassmannian as a representation of the Yangian, this geometric representation theory construction constructs this as a tensor product of two-dimensional representations. And then if you look in the operators quantum multiplication, they belong to this Baxter subalgebra parametrized by the data which is interpreted as this curved contour parameter. Maybe I'll in the so maybe I don't know, maybe it's too late in this lecture to start. So so at this point you should be somehow, the next step, the next logical step is to start building up this framework. And of course for SL, for this particular representation, well, after all, Yangian of JL2 is not such a complicated algebra. You can see that this is the right answer. You can see that this belongs to the algebra it should belong. But maybe a more satisfying way is to have a more conceptual understanding of why something like this is true. And this more conceptual understanding, it has to do with you see that this is Yangian is a Hopf algebra. And I didn't explain what a Hopf algebra is, but I will explain that Hopf algebra is different from plane associative algebra in that its representations, you can tensor multiply its representation. And in fact, we see that this is somehow tensor space. And actually, the main logical step in some highbrow proof of the fact that this is correct answer is to think geometrically about what this tensor product means. Maybe we'll postpone it and instead just re-examine what the very old, somehow after all, in this particular operator was diagonalized by Hans Bethe, like I said, almost 100 years ago. And he found some equations called the Bethe equations that describe the spectrum of this operator. And these beta equations in particular also describe the spectrum of this operator. So in particular, they describe the spectrum of the quantum cohomology ring here. And so maybe I'll postpone the general discussion. We first discuss the answer for the spectrum, and then this particular will describe the spectrum of the quantum cohomology ring. So maybe we'll do that. And since it's kind of the easier, lighter stuff. So a reminder. So if I take the spectrum of quantum cohomology of Grassmannian itself, Kn, this was given by the equations that I have as some variables xi, which raised to the power n were given -1 to the k - 1 times z. And it was the condition that xi, xj are distinct. And so this is like, these are for projective space. For projective space, we look at root system. We look at the equidistant points on the absolute value of xi is z1 on n, and then they have to be this for projective space, and for Grassmannian we have to choose a k-element subset of distinct points. Now, if I look at the spectrum of equivariant cohomology, the Grassmannian, again, then okay, this was described. So this was the set of. You also had this k variables equals xi. I ranges. And now it has to be the case that xi's. So now the condition is that xi's, again, they're distinct and form a k-element subset, a k-element subset of the set of k1 to n. And right, so this is all everywhere we're quotiented out by symmetric group. This is up to permutation, and because this was arrangement of hyperplanes. Each hyperplane corresponded to a particular subset here. It means xi up to permutation have the fixed equal to that subspace. And now there's the equations. They're equations for the spectrum of the quantum cohomology of this Grassmannian of covariant Grassmannian. And the way to write them, maybe I'll write the answer, but then I'll try to explain how to abstractly write them for any like a Gemma variety at least. So then this will be saying like this, so you take the product. So first there will be equations in they will involve AIs, Z, and also the variable H bar. And the way it goes is like the product of J from 1 to N. So maybe the way to write this equation is really you take the product of for any I, the product over J from 1 to N, x minus AJ, this is 0. Now maybe xi's. Let's say xi's to be, if xi's are the churn roots of the dual tautological bundle, then that should be minus here. So then we take plus. That's great. If I pose this condition and I pose this condition, then I'm getting what I want. And so now this becomes like this. So if I take the product over J from 1 to N, take this like before xi plus xi, well, maybe I'll divide xi minus J minus H bar, then the product xi minus H bar, xj minus xi minus H bar. This is equal to 1 minus k minus 1 to z. And so there are two observations about it. One is that this is slope invariant. Slope means a change of stability condition for T-star Grassmannian. For T-star Grassmannian, if you change the stability condition, the numerator and denominator get exactly exchanged. And also the curve class under Flope naturally goes to one minus curve class, so you get 1 over z. So if I take 1 over both left-hand side and right-hand side, I get the beta equation for the Flope. And then second, go into equations for, so the common generalization of this equation is when I replace the z. So in general, the quantum equation is like this. And then and they go to this in the limit, go into equations for Grassmannian. This equation, if H bar goes to infinity, and I take z mu, I declare to be the z old divided by minus H bar power. And why is this correct thing to take? Is that because the computations, how do I recover quantum cohomology of Grassmannian itself from the quantum cohomology of the cotangent bundle? If I can localize with respect to H bar. So if I take if I look at M0 to X bar with respect to C bar, so H bar, what it does, it just scales all cotangent fiber by H bar. So the only way a map can be fixed under this if it really sits inside. It really sits inside Grassmannian. Grassmannian. It doesn't have to be 2 mark points, any number of mark points. Okay. But these abstraction theories, of course, are not the same. Abstraction theory. So if I have, so if I have my Grassmannian, and I have a curve in it, then I have to think about the cotangent bundle. So I got T star, the tangent direction. And so there's this, they all get the weight minus h. And so this, if I looking at the virtual cycle for x, I apologize, I don't want to copy the whole thing, I just put x. This is for x. And let me know. This is too slopey. Maybe I'll take this guy and I put the virtual cycle here. And this is the virtual cycle there times the Euler class. So Euler class is Euler class of a vector bundle is well, it's top exterior power, and so then when here I have to put, since I take the deformations go in denominator and the abstractions go in the numerator, I have to put the minus sign here. So minus cohomology of the pullback of the cotangent bundle. And this whole thing gets a weight, h bar inverse. This means this whole thing, what does this mean? It means I have for every abstraction I have like minus like a product over h1, some weights in h1, I get an expression like this, and a product over weights in h0, I get an expression like that. I get an expression like this. So if this has some weights w, then this means if this bundle has Chern roots w, then this Euler class will have this expression. And its behavior for large h bar is going to be asymptotic for minus h bar to the rank. So maybe the minus the rank. Minus the rank of the cohomology of pullback of the cotangent bundle. And so what this thing will be? This thing will be so this number, this rank by Riemann Roch is equal to the dimension of its rank, so this dimension of the Grassmannian, plus d times its degree, which is you pair d. So the first Chern class of this bundle is minus the first Chern class. So put the minus the first Chern class of the Grassmannian, which is the number is n. Okay. And so this says that this in degree d, I'm going to get an overall factor of h bar, which goes like d times n. Which means I have to, my variable z, I have to rescale like this. So if I rescale my variable z like this, and I send h bar to infinity, then I should recover. Then the quantum product for Grassmannian is gotten from the quantum product for T star in the limit when the equivalent rate goes to infinity, such that you have to rescale these. the curve counting variable. And this is correct. And the way to write this equation, so this is for general, this is, so how do you write this? How do you write the spectrum? Oh, right, and then how do you write these equations for general x? It's a very beautiful formula for this. So maybe I'll write this formula, it'll be the end of the lecture. General answer. Spectrum of quantum topology for any integerable variety. And this is what Nekrasov and Shatashvili really computed. I'll explain how this computation is done. When they've computed it before, when they compute on the physical level, rigorous, completely rigorous. Also on the math level, rigorous, completely rigorous, except there's some details, like it's only recently been proven that in fact the cohomology of Nakajima variety is generated for general Nakajima variety, in fact the cohomology is generated by the Chern clouds of tautological bundles. So if I have a Nakajima variety X, so if I have so maybe what I have in mind is there's a proof by McGurts and Nevins. They say in general that this is what's this has been expected, but with no proof. So they say the cohomology, Crane cohomology of Grassmannian generated by Chern classes of tautological bundles. We call them VI. I ranges over the vertices of the Dynkin diagram. This means that the spectrum of ordinary current KT of X, this embeds into you have some variables. You have the variables for the Lie algebra of the source T. And you have some variables for, so this VI has Chern classes, Chern roots. Maybe call them X, I, J, where J ranges from 1 to the rank of VI. This rank of VI is usually denoted with little VI. So times this, you have these variables, like what do you have, like x1, 1 to x1 v1. This is modularly symmetric. And so this thing is embedded in some maybe this. This is like for Grassmannian, you have several such factors. So in particular, and also in similarly for key theorem, for invariant K theory. For invariant K theory. So in the covariant K theory, in particular, you have a very special element, the tangent bundle. So this tangent bundle becomes some symmetric polynomial. It's not particular. So what does it mean? It means that you have the specific symmetric polynomial in this axis xij, whatever ai in h bar. Like, what is it for Grassmannian? For Grassmannian, T-star Grassmannian. G. For X, T-star Grassmannian. What is the tangent bundle? So this is T-star Grassmannian. Well, we've discussed that this T-star Grassmannian. This is the space formed by pairs CK. I think it's known as A, and this is B, CN. And this is my, so maybe I'll just know just V. So this is the fiber of my tautological bundle. This modulo K. And so the Chern roots of the tautological bundle, they're really this x1 xk and my G. And my maybe I want to take the dual tautological bond, so I put inverse. These xi's are Chern roots. And then my torus A, well, I guess there are two different A's, but I'm not too late to change now. So the torus attacks here. And so what's the tangent bundle to X? Well, it's written here, right? So then it's, in satisfying the condition is that BA equals 0. So first there's A. A has the character of just summation. So AI xj. A is an element of CN tensor V dual, and so the character of my group is this thing. Plus B goes the other way, and it's scaled by H bar inverse, since this is summation. The dual thing is this. Then I have to impose. Then I take out the tangent bundle to the group. So this means I subtract xi xj. This is the character of this is the character of Lie algebra of GLK. And if I think where the moment map takes place, well, the moment map takes place in the exact same space with the exact same character, except the moment map has an extra H bar inverse in it. So really it's 1 plus 1 over H bar, or maybe H bar inverse. You see, it would have been much better if I denoted H bar inverse by H bar, because we just keep writing H bar inverse. It's a waste of chalk, but it's anyway. So this is for the equation. This is for the equation BA of 0. So this is the expression. Of course, while in general you can somehow just from the quiver description, the tangent bundle to any Nakajima variety has this similar expression. You just read it from the quiver data. You just read it off. And so now the formula. The formula is there has to be as many equations as you have xi. So for every, it has to be equation which is has to be zero-dimensional over this base. Right? All of our the Korean K-theory, Korean homology, and so forth. It's all maps finite to one to the base, to Korean base. It has to be for every xi we need an equation. And the equation look like this: that for any I, we take the Euler class of xi for every maybe ij, xij d by dxij of the tangent bundle. That's some expression in K-theory. You can take this derivative to be some expression. You take its Euler class, and this is equal to the corresponding. So for every one of the vertices, there's a weakness I, and so then indices I correspond to you have as many degree counting variables as you have vertices in the Dinkin diagram. And so then you put the corresponding variables at I here. Right? Concretely, what is going to be for Grassmannian? For Grassmannian, if I take, so xi d by dxi of my tangent bundle, well, there is, I should have written j and I. I. So this would be summation over j ai aj times xi minus, as this guy, the other guy is going to go in denominator, minus 1 over h bar aj xi. Now I'm going to get minus h bar, minus 1 plus h bar inverse times the summation over j. Now every time, so this, in this expression, I go for every xi in j, I get the pair I xj, and I get also the pair xj xi. And so this one will give me plus, the other will give me minus. So it's going to be xi over xj minus xj over xi. So what would be the Euler class of this? The Euler class of this, and so I didn't introduce a separate variables in cohomology and K-theory, so I'm going to use the same variables I use, I denote the logarithms of the variables by the same variables. So I hope it's okay. So this will be, this means I take the product of the corresponding covariant weight. So it's going to be a product over j of aj plus xi. Now this one comes with the minus sign, and so they will go in denominator, so it will be 1 over, and they all come with the 1 over, so it's going to be the product over minus h bar minus aj minus xi. Now here there is a part which has h bar, it has no h bar, so without h bar it's going to be, since this is with the minus, is going to be xi minus xj, and then there'll be xj minus xi. Right? This whole thing, I mean, this is minus 1. So this whole thing will give you this minus 1 to the k. So this, in my beta equation, there was minus 1 to the, sorry, k minus 1. There was minus 1 to the k minus 1 sticking in front. This comes from this part. And then the next part is the, so xi minus xj minus h bar, xj minus xi minus h bar. Okay. Does that make sense? This whole big thing has to be equal to z, and this is just a big direct equation. This is an exercise. You can write the same thing for the Hilbert scheme of points and check that this, in fact, does give the eigenvalues. This is not trivial. I mean, it requires either. So, the fact that you get the eigenvalues of the operators as stated. So, what does it mean? It means this is my particular operator. The particular operator I wrote down was a quantum multiplication by the first Chern class. Means you take the variables satisfying this equation, you sum them up. That's kind of non-trivial, but it's true. And, all right, I'm again out of time. Oh, sorry, a bit again over time, and for which I profoundly apologize. That's it for today. Yeah.